Alright. So last time we did 31. I'm going to take a stab at a handful of these 30s problems. So this is what we're looking at. Here's a very brief conversation on binomial coefficients. They define it this expansion where mu is any number, but if it's positive, you can interpret it as the number of combinations of mu objects taken r at a time. So then, got a pretty straightforward, well, he says to prove this multiple ways. I guess that makes it more interesting. And then a few that are kind of tricky, which I don't think I was familiar with these identities before. And 34 is a bit silly. 34 is kind of an obvious one. But I haven't done 34.1 or these other ones yet. So I'm not sure how far we'll get today, but that's what we're on. So 31.1. He says to prove this a few different ways using combinatorics or using binomial theorem or neither, for instance. So statement is probably something like this. And choose R is the same as this. So if you want to use combinatorics, if you want to think of this as counting, that approach would just be that, like, when you choose R objects from a set of n, you can either include that object or not. So let's say you have a bunch of objects like A1, A2, up to AN, right? And we choose R of them. This is the same as you either include one of the items, let's say A1, and doing the same procedure. So we're still going to choose our items, but we either include the A1 in the selection, meaning you still have another R minus 1 to choose out of the remaining items, which is n minus 1 items, or you're not including it, in which case you're in this situation where you still have to choose all R items because you're just avoiding that A1 item. That's about it for the combinatorics approach. So this identity makes sense. Let's see, if we use what is going on here? There we go, something like that. If we use, well, you could use the binomial theorem. Trying to think if I need to. like if you put 1 minus z, or sorry, 1 plus z, say, to the n, that's a typical way to get these coefficients popping out. Right? Okay, well, we could also write this as 1 plus z times 1 plus z to the n minus 1. So that's how you're going to get a change in coefficients. This is now n minus 1. Choose r, as r goes from 0 to n minus 1, like that. So if you do 1 times that, you're getting these coefficients back, and the index is the same. Maybe it'd probably be smart to like take off this last term. This is the same as going from 0 to n minus 1, and then adding just the case z to the n. I'm wondering if that's going to be helpful. Okay. But anyway, so yeah, when you do this, you get itself, and then you add z to it, which sort of scales the, so we still have the same term here, but I multiplied by z, so when we reindex this, it's going to alter this r value. If we just subtract 1 from all the r's, so here when you plug in 0, I guess you get 1 z, like this. This guy is z plus n minus 1, choose 1, times z squared, plus n minus 1, choose 2, z cubed, da da da, and it stops at 1, it stops at z to the n. Though the previous one is n minus 1. N minus 1, choose n minus 2, I suppose, but so this part you could reindex as I mean, I was just going to make them z to the r, but now they start at 1. Yeah. They end at n. So if you change this, if you reindex this, you're getting this part. But it ends at n. So we should do something about that because they don't quite match up. I mean, I suppose you could put a 0 here with the understanding that it doesn't make sense to do n minus 1, choose negative 1. This one's still the same. It ends at n minus 1. So we started with this. I mean, I suppose we started with this. So I know this is true. I'm just trying to make it match up exactly. This part's fine. This part, if we take off the last term, right? And I guess there's really not too much to say. We've basically shown it. I was going to say you could just do this and ignore the case, you know. So there's two things happening here. You can pull the the plus z to the n out, which I will do in a second. And then the other issue is like, well, are you able to plug 0 in there? We'll just say that this equals 0. Doesn't have a lot of meaning. So I'm going to assume that that happens, and then it falls through without an issue. And then the last case showing this identity is you could do it directly from like the definition. So if you had n choose r, that's this, and we want to show that it equals the sum. Oops, r minus 1. But if you just write these out, I'm sure it'll pop out. So upstairs we have this same thing, but we're gonna have different denominators. Down here we have an r factorial. Over here we have top minus bottom, n minus 1, or n minus r minus 1, something like that. Right? You usually do n minus r. So this is n minus 1 minus r minus 1. It's a lot like n minus r. So this is missing one factor, and this is missing one factor. If I want to add these fractions, I'm going to put an r upstairs and downstairs. Like this first fraction is missing n minus r, and this second fraction is missing just r over the common denominator of r factorial, n minus r factorial. So kind of quick fraction thing is easy to show that this is true. If you just look at the definition, this is becoming n minus 1 factorial times n over r n minus r factorial. And so we have shown it. This right hand side is exactly that. So that's it for, I guess this was 31.1 maybe. 31.2, prove that this series of differences is equal to -1 to the r times n minus 1 r. I don't know that one off the top of my head. I think we're doing this. In general, something like this to the r and choose r. Maybe I screwed it up already. Let's look at this again. And then it equals an alternating term with n minus 1. It looks like we stopped here too. So it was like a finite thing. We didn't actually go all the way up to n. Could replace this with the thing we just used, and then that would kill off this one term, and we would have this choose r minus 1 with a negative sign. I don't really see that helping me. Although I guess this previous term would be almost the same, except the top would be n. But there's a sum of a bunch of other things. What else can I do with this? like it, I mean, other than the fact that it's finite, it sort of occurs to me that this is 1 minus z to the r to the n. You'd get a bunch of these, although we're missing a bunch of terms, but you'd also get negative z to the r, like that. So if I evaluate this at 1, you should get 0. But also there's extra terms here, so we do get the beginning. We get up to here, so we get the left-hand side, and then we also get like r plus 1 and choose r plus 1 da 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 up to that, basically. So if you sum these, you will get 0. So is it possible that this junk is equal to this with a, with an extra negative term or something? Don't love that. So that was one thought I had. Let's attempt one. It's a little sketchy here on the right. I guess another thought that I had was that you can replace this. We could maybe replace this with this guy, if you want. I don't know if that helps, but at least it matches up here, right? So that tells us, well, we could then add this term. It tells us that subtracting that off, we get the previous term, r minus 1, and choose r minus 1. And then we can add this term. And that also equals 0. And it has this guy. It was an extra negative sign, so now it still has this guy in front of it. And it sums to 0. I don't see that helping. So those are my only two observations. There's got to be something that I'm sort of missing. I mean, I was able to get these by doing this kind of expansion. Except that it's not finite, and then I was looking at this chunk. happens if you look at this, right? And then we say, well, or put k's here and look at the rth coefficient. That'll give you this. Like, replace this with k's. And then look at the particular case, the rth coefficient of this is our right-hand side, of course. If you multiply this by like 1 minus z, of course you get this stuff, but yeah, it changes this whole thing. I was gonna say maybe our coefficient can be split into multiple pieces based on that. Yeah, unfortunately this changes the like the rth coefficient no longer represents the same thing. So yeah, if you multiply by it, you get a different series. How does that help me? I think I'm missing something obvious, I guess. So, of course, we still remember that we just saw this. I had thought of that here, like replace the right-hand side. And then you get this statement, which, if I could show that that were true, we would be done. Well, something kind of odd happening here. Like, this is basically this minus that, or the other way around. This right here is a difference with the, matching R. It looks like this kind of collapses to a smaller term. Like I'm saying, this junk is the same as like if you factor -1 to the R minus 1 out, you're looking at this, which we know is, which we know is n minus 1 r. Wait, you go up? No, I think it's r minus 2, actually. You could just keep doing that, right? Because this term, no, I can't, because the numerator is n. No, yeah, it's going to be the same thing. It's the numerator on the previous term is an n with an r minus 2. Like, all of these are, previous term is, negative 1 to the k and choose k. So you could probably do that all the way down. That was a little hand wavy, but suppose you do that all the way down to like, you're down here at like this, and then this would be a different term, but it would be n minus 1. And what do we say? We said it matches, so it would do something like that. Right? It matches the part on the bottom that you're choosing. It's just one less in the numerator, in the top part. So you'd get something like this, which is which is what? So you can decrease this, and you'll be swapping this with that minus that. I'm saying it's, I'm saying it's this? Yeah, that's evidently what you're saying. This minus that gives you decreasing in both of them. Yeah, this is what I meant. Wait a minute, is it the opposite? No, it's what I wrote. So I don't get 0, right? I get, oh no, I do get 0. 1 minus 1. Alright, so using this works. That was a little sloppy. Let's see what he said, because this was a mess of an answer. 31 point. 1 was the one we just talked about a minute ago. Oops, here you go. We're looking at 31.2. It says, it just says use induction. Okay. Oh, yeah, that's kind of effectively what I did. I didn't actually use induction, but I'm saying I noticed a inductive relationship. Like, if you start at, say, n, well, if you start at, say, r, you can work your way back. We could also just do it by induction, properly, if you like. So you'd have to notice, like, one example. Here's the base case, maybe. Are we getting... Yeah, we're supposed to be getting that this equals... Actually, he didn't say to do this. He said to do induction. I guess we could do it on n, right? I was going to do it on on r. Yeah, let's do it on r. This is obvious, right? For some reason I'm not seeing it. Oh, yeah, okay, of course. This is 1 minus n. This is the negative of n minus 1. So there's your base case. And then if, suppose it were true that that like that this happens, can you show that it's true for like r being increased by 1? Or, like, well, we've got our formula again up here. You can pass to, like, this is the same as n choose r minus n minus 1 choose r. So if you want, I'm not going to negate everything. This is still as it was. I guess we could make it r plus 1 if you like. That won't break anything. But anyway, this part is n choose r minus n minus 1 choose r. The right-hand side is good. It's got an extra, yep, the right-hand side is good. There's just this extra term, which if I add to both sides, you get r plus r, you get r here. So left-hand side, this term is there still. And then if we add the last term, it becomes an r with n choose r. And the right-hand side is, an extra negative. See that? So that's it. That's the whole proof. That was induction on R to get 31.2, along with, you know, the obvious that we got from 31.1. You need to know this, or it doesn't work. Okay. Intriguing. All right. That was 31.2. We're on to 32, which is some squares. Some of the squares of these things is 2n choose n. Then 33 has got something similar. Well, no, it's got 2n there. But the right-hand side ends up being almost the same, except for the alternating bit. I tried these the other day and I got stuck and I ended up just looking, and he's expanding, actually, yeah, he's just doing what your instincts might say to do. I think he's saying like take a binomial theorem and square it. The reason I didn't try that is because I knew I would get a bunch of cross terms that I didn't know what to do with. And then down here you're doing something similar but with like a minus sign. So I'll try something first before I look again, but I'm not remembering it very well. I think we have that on the left, and he wants us to show you get 2n choose n. Pretty sure it was that. Yep, that was one of them. And then another one is, well, the top is 2n. 2n0 minus 2n1. Oh, these are squares. Da 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 da. 2n minus 1 squared plus, so it does go all the way up to the end. And on the right hand side you get, I forget. Is it 2n choose n? Yeah, it is. Alright, so the alternating bit. So this is just one coefficient, if you think about it, of this mess. Like some series could have this as a coefficient. if we're doing 2n, choose r, similar to how we approach 32. So I think 32 and 33 are going to be very similar. Like, if I did have this series and I just square it, oops, sorry, z to the k, I sort of wonder what happens. I know that that's the same as this, and that would give us these terms. So I wonder if we can just find the rth term, or the nth term here, something like that. This is 2n, choose k, z to the k goes from 0 to 2n. But over here, you're getting sort of a double sum, right? You're getting these, and then these again. Whatever, I'll just write a square. So you're getting z to the 2k. Like, what if I had j from 0 to n, and like l from 0 to n, and we have n choose j, n choose l, z to the k plus l, right? Oops, damn it. j plus l. Okay, it's evidently the same as this. So if I did make these match up, like if we did have that k is j plus l, yeah, this kind of bugs me, is I don't just get the one, I get like this times a whole sum of these. So there's like many terms where the j is some fixed number, and then this changes. And I guess I'm just ignoring them because I only want one. So let's not call it k. Let's call it like, well, I guess we want the nth one, right? In particular. That might actually be special. Because it's like right in the middle. Yeah, it's not just any. I actually want n to be equal to these. That'll give us, so we're trying to show that you get, on the right hand side, of course, you get 2n choose n. On the left, if this happens, well, you get the same quantity, don't you? Right? You get the same number. So you are getting squares. That can't be right. Yeah, it is right. Huh. Okay. So it just so happens for this particular value that, like if I replace L with n minus j, right? This series is, this coefficient in front of the z to the n term is going to be like this. And these are equal. So you are getting squares. They're always squares. That's interesting. Okay. So some of the terms that you see here, there's other stuff too, but the one that corresponds to the nth coefficient on the right hand side is of course that. the nth coefficient on the left-hand side is a sum. Well, it's really like a double sum. So we've replaced. Is it no longer a double sum, I guess, because I did this? Not quite. I guess I'm just a little confused by the other terms. They don't all do this, right? We started with this. And we could write a few out if you want. Yeah, so we started with this double sum. And I'm trying to just simplify the way it looks. Like if you wanted... Like if we replace this with a k, here of course you get k minus j. That might be a lot clearer. And then the k, it's k minus j that goes from 0 to, so k goes from j to, it's confusing. You can do that, is what I'm saying. I just did the same thing, but with a k. K equals j plus L. Means L is k minus j. Yep. But L still goes from 0 to n. So, I replaced like L with k minus j. So k minus j goes from 0 to n. K minus j is n. I guess this would be j plus n, right? Oops, n. So you do get a bunch of wonky guys. That's kind of what I was expecting. Like you get cross terms that I don't want to deal with. But if you if you do look at in particular the nth coefficient, so where k is n, then you're looking at it's not that j is 0 all the time, it's just that right. It's not that j is 0 all the time. You're still doing this double sum. Like when j is 1, you get 1 plus n minus 1. Or I guess I should say that when j is 1, the this is n minus 1. Anyway, this is the same. This is our left-hand side. This is the series that we had when you square it. This is another way of writing it. So if you take the nth coefficient here, you're letting k be n. And I guess you just get the one sum. Yeah. We're letting k vary here. Maybe it would have made more sense to put this on the outside or something. It's fine. It's fine the way it is. But we're looking at one particular value of k. That's the nth coefficient. And we still get a sum. We get j going 0 to n, nj, and n minus j, which are equal, by the way. And that's it. It's all this stuff in front of the nth. That is the nth coefficient. Okay, and they were all pluses. There's no alternating going on there. So this is correct. This is the end of the... that's this sum. It's the same as this. Because n choose j is the same as n choose n minus j. All right, so this first one does happen if you just square the binomial theorem. Like if you look at this series and you square it, you do indeed get this. So if you just look at their expansions, you'll see the nth coefficient will give you this statement. This one, I'll bet, is the same, because the right-hand side, that's how you would get it. Again, just put a minus z here. So if you had 1 minus z to the 2n, that's the same as this. Oops, let's put a k here. Negative 1 to the k, z to the k, right? To 2n. So if you look at the nth coefficient of the right-hand side, that's this. Negative 1 to the n, 2n, choose n instead. So we're going to do the same trick. 1 minus z to the n. If you square that, what do you get? You're going to get a double sum. And we'll just look at, in particular, the nth coefficient. So I won't worry about all these weird cross terms. So you get, if you want, we get, let's say j goes from 0 to n, and L goes from 0 to n, and you get n choose j, n choose L. I guess the negatives don't cancel exactly. You get j plus L, and you get z to the j plus L. And now I'm curious what happens when you well, before I had done like a reindexing first to make it a little easier on my brain. So like, this is the same as k going from j to j plus n. And then here you get something like this, right? And then this is negative 1 to the k and z to the k. And now we let k equal n and see what happens. If you fix k as n, on the left here you'll get a sum. But again, these are the same number, so you're getting just this squared. This time you also get this negative sign, and that's what's in front of, that's the coefficient. If you sum over all these, that's all the coefficient of z to the n. Those are different ways that you can get terms that involve z to the n in this double sum. So we're getting, 0, sorry, that term. Wait a minute. Why are these two n's? Yeah, he definitely wrote 2n, not just n. Hmm. Hmm. Yeah, I basically just showed the same thing again, but with a negative sign in front, right? This was not very interesting. This is just 32 again, what I just did. Um, hmm. Yeah, I'm pretty sure he wrote two n's there. I don't think I... Yep, he did. Yeah, I'm not sure on that one. Let's take a look. Oh. So 32 is fine. Um, yeah. It looks at z squared. Uh, he does this. Well, he didn't really do that though, did he? He did this. And he gets this. Okay. Huh. So yeah, we're trying to show this up here. Um, this one is, of course, 2n, like, it's just that. The one next to it has got an alternating bit. Oops, that's a 2n. And then we know that this would equal, say, 2n, choose k. You get an alternating bit, but then you get z to the 2k for some reason. I guess that doesn't matter. Or does it? It matters a little bit. Because we wanted in particular n, so we're going to let k be n. So we're going to be looking at the coefficient for 2n in this expansion. But that's fine. Isn't that just the last term? Well, no, because there's a product here. So one of them is the last term. Like, that guy. And this guy is maybe also from the other one or something. Huh. Okay, sure. So if I did rearrange this the same way I did before, we get like 2nj, 2n, k minus j. Oosh. Sure you want to do that? Well, it's too late. I did it. And then z to the j plus l is k. Oof. Anyway, we want to let k be 2n, which we can do. There's multiple ways that happens, of course. So like if this was 0, but L was 2n, that's one way. That was the way I was just thinking about. But this is, 2n plus 1 different ways for it to happen. All right. So at k equal to 2n, these are identical, and you're just getting 2n, well, I'm just going to call it j again, but you get that squared. And you also get this to the 2n minus j. Sure, that's it. This is the coefficient that we're looking at for the 2nth term, the z to the 2n. And it matches this right-hand side. It's -1. Yep, -1 to the, well, on the right-hand side, it's actually the nth. It's still the 2nth coefficient, but this value for k is n. So that's where that came from. And this is 2n, n, like that. On the left-hand side, you get a sum, but it's alternating. It's 2n, 0, with a positive sign, and then it alternates. Yeah, that's it. All right, 33 is not bad, but I would not have thought of this trick. That's basically what you'd have to look at. It makes me think there's probably more of these, like what if you look at a cubic and you still look at the nth coefficient? You'd get triple sum, which is maybe not as nice because it simplifies to a double sum in the coefficient. All right, let's see what 34 looks like. Oh, 34 is an easy one. 34 is a good one. 34 is like pretty basic series stuff. It says, suppose you take a product to infinite series and you get this. So the CNs are the coefficients of your product. And they want you to deduce basically formulas for the CN and the gamma n. The gamma n is very similar, it just has a factorial downstairs. So maybe part 2 here with the factorials looks more like you might see a Taylor series situation happening. Actually, I'm pretty sure it just follows from the first part. So if you had, looking at 34 here, if you had like ak z to the k times bk z to the k, sum is ck z to the k, find a formula for ck. Okay. Well, let's right? Anyway, when you add these, of course, you get j plus L. So we're going to do a substitution in a second where we just let k be j plus L. And what goes here is aj bl, but they're still sort of all over the place, like that. So you're getting like every possible combination. Now I want to look at just the ones where the power here is k, meaning I can replace this with k minus j again. I suppose that means L goes from K goes from J to infinity, I suppose. Why not? I think we can do it that way. This is bk minus j, and I think we're basically done. So starting at j, you get b0. Were these not finite series? Oh, you just want the nth. Yeah, I see. They're not finite, but we're only going to take a finite number of. So, for instance, if k was n, the coefficient of the z to the n term, you're still getting a sum as j goes from 0 to wherever it stops being relevant. I guess like once this drops below 0, right, you're getting 0 for this product. Like if it was b sub -1, that doesn't make any sense. You're getting a 0. So you sort of get a0 bn plus a1 bn minus 1 all the way up to that guy. And after that, there's still terms. It's not like there aren't higher. It's not like there's not more terms for the AIs or for the BIs, but they're just not relevant for this conversation. So there's your formula for CN. And then if you do the same thing with, I don't know, like alpha j over j factorial, something like that. And then you have got like beta L over L factorial. Again, 0 to infinity. And you said that this equals a new series, gamma k over k factorial. And you wanted to find a formula for gamma n. You can actually do it exactly the same way. We're going to know that gamma n over n factorial is just this formula, but with these guys. So it's like alpha 0 beta n over n factorial plus alpha 1 beta n minus 1 plus alpha 2 over 2 factorial beta n minus 2 over n minus 2 factorial, and then 3 n minus 3, etc. all the way up to something like this. So we're just applying the previous result. And then if you multiply by n factorial, yeah, if you multiply by n factorial, you're getting a bunch of like combinations, right? So over here we get like n choose 1. Here in effect there's an n choose 0. This is n choose 1 because it's just n. It's the only thing that survives is n, and then the n minus 1 factorial gets canceled. So there's an n choose 1, alpha 1, beta n minus 1. This one's n choose 2, and you put n factorial on the top. Da 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 da. Anyway. So yeah, they're both sums. Cn sum kind of looks like this. Gamma n sum looks the same, but it also involves these combinations. That would be my instinct. Did I screw that up? No, that's right. So yeah, there's not much to prove on that one. This one I haven't looked at. So I think we might make this the last one of the day, this 34.1. I don't know, maybe I'll take a stab at 35 too. But 34.1 says you're given AIs, define Bn as this sort of alternating series with combinations, and derive almost basically the same formula. This is sort of an intertwining between the ANs and the BNs if you define Bn that way. So AN would be given by the same formula that Bn was if you do this. So if you're given an infinite sequence of ANs defined for a natural number n, Bn is A0 minus N1 A1 plus N2 A2 minus da 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 da, alternating terms, and it looks like it stops at AN. Show that AN is exactly the same formula. Well, so this is an alternating sum with n choose I, a to the I, right? It's a finite sum. That's what Bn is. So if you look at this again, let's go to like, let's go to n of not these terms, but the b's, like same expression, but I'll put a b here instead. Oh, I didn't mean to the power I meant downstairs. So yeah, I want to look at what this would be. Yeah. it would be a double sum. Starting to get pretty sick of those. Alright, the bj would be this formula. It stops at j. Sure. And instead it's j, choose I, unfortunately. A sub I. So that's an expression for b sub j. And my big question is, does this give you back an, I guess? Wait. Yeah. Yep. I can't get rid of this. Alright, so 0 to n. Yeesh. These, of course, add, and like, you've got two terms now, nj, nji, and the ai is still here. So I haven't done anything. I've just been shuffling stuff around. Yikes. Yeah, yikes, indeed. If, so when, this doesn't make any sense. What are you doing over there? I goes from 0 to j, huh? So one thing I was going to say is there is a point where j equals n. And that's the one time that we do get an an term. Obviously this is no good. We're going to swap this order. I just thought I would be clever and move it to the outside, but I guess I could try to change that if you want. Like we're saying j goes from 0 to n. I mean, you could also just look at it like this. J goes from 0 to n, and I is less than j, right? So it would be the same if you want, you can do j is greater than I, while I goes from 0 to n. Same thing. J is also bounded by n. So if you wanted, we could change this. Like, this could be an I, this could be an n. Actually, yeah, I goes from 0 to n. And j goes from I to n. It should be the same, same series. Don't know if that's going to help me. I'm just poking around. So what I was going to say is there is a term when I is n. I guess when I is n, j is also n, right? So this is gone, and you're getting just 1. So there is an an term on its own, plus some other stuff. Does this all stop at n? I don't see why not. Yeah, it does. That's fine, because it doesn't actually affect the AI. So we got the one term where an is there. So I guess if I was able to show that this was 0, that would be the same thing, right? And j, ji, and there's still a bunch of AIs here. So if you're able to demonstrate that somehow this is 0, that would be the end of this proof. I don't know why I would know that. Probably thinking way too hard about this. What are these terms anyway? When I is 0, you get, oops, didn't mean 1, I meant I. There you go. When I is 0, you get, I don't know, you get a bunch of stuff, actually. So what's in front of A0? It's the sum from 0 to n. These do alternate. You get an alternating thing there. This is n choose j, but j is changing. I is not, though. This is always 0, so that's not there, and you just get A0. Then, when I is 1, you get 1 to n, alternating but a different sign. I guess I could have put a minus sign here if you wanted to match that up. This part's always the same. And then this is a j. And that's A1. And then on the last term, n minus 1, you know, sum from n minus 1 to n. J plus n minus 1. Yep. Okay. J plus n minus 1. And then n choose j is always the same. And this part is finally, I mean, I guess it's just a j again, right? It's j choose n minus 1. Yikes. But I guess there's 2 terms there. So better write it. J choose n minus 1. A n minus 1. Yikes. Now you can get rid of the alternating bit by like actually just including it out front. want to do that. But, yeah, this is probably a weird way to think about it. There's probably a much faster answer to this. Just look, like, you can just use this, I'm sure, or this guy. Where's the other one? This one. Like, this is this product where the betas are like alternating, right? Just plus or minus 1. That's what you got here. That doesn't really help me. Can you then show that the alphas are just an alternating version of the betas? Strange. Yeah, we didn't know any other conditions about did they maybe cancel and I'm not seeing it? Are we gonna get like, you know, B0 minus B0, like some sort of telescoping thing in the BNs that just results in 0? This one actually is BN, right? Yeah, this is BN. This one's missing a term. Oh, wait. This is not BN. Huh. Because it doesn't have all the A's. But you can see how I got there. This does contain BN. No, it doesn't contain that last guy. So it's basically just Bn minus An. I pulled this out. Huh. I think I'm going to miraculously pull this starting point out again. Probably, yeah. So yeah, that's not true. But sort of, yeah, it's part of it. It just also contains a bunch of other stuff. Alright, I'm in the weeds on this one. I guess I will go ahead and cheat. 34-1. What the heck? What? Would not have thought of this trick. He says e to the x times an alternating version gives you back Bn. And therefore, yeah, I would not have thought of that, obviously. He's saying if you took x to the n over n factorial and you multiply by this junk, you'll get our series, and that'll imply the same thing with the an's and bn's swapped. Looking at 34.1. So this is the second case, of course. This is this one. That if you have two infinite series like this with factorials in the bottom, the formula for this guy is here, I'll just pull it out again. We got a bunch of ones in this case, but other than that, we start up top and we sort of decrease, and you also have the combinations. So in our case, it doesn't really matter which direction you go with this, but you could write it as a 0 minus a1 over, actually it's not times 1 factorial, this should be times n choose 1, like that. So it's n. So plus n choose 2, a2, etc., all the way down to -1 to the n choose n, a n. That was what we were given, isn't it? Yep, it is. Sure. So he's saying if you just multiplied this junk, -1, the alternating a to the n times a 1, you take this product, you do get this. I agree with you there. That has the right definition for the bn's. To get backwards, he's saying look at the same thing, exactly the same thing with alternating bn's. And you'll observe that this happens. From this, it follows that this. I'm with you on the first step. I mean, okay, so obviously this is just going to say the same thing again. Like, if this line is true, then we're done. Um, oh, okay. It is obvious, isn't it? This is e to the x. If you put e to the negative x over here, right, times this, um, you just want to show that that's, well, this part is alternating, right? Yeah. Well, this stupid alternating bit in the way. Yeah. Hmm. So he points out that this product gives you this series, which is true by hypothesis. Um, and then he says, well, look at this. You would get the ANs. Like, that's obvious. What's not obvious to me is that this should equal that, like, it's got to be this, right? It has to be. Like, if I multiply e to the negative x on this, you this. I'm just confused because wouldn't that just mean that these are the same series? Yeah, no, it doesn't. It means that kind of means that these are the same series. I'm so confused. Well, I'll tell you what. We're going to call this a good place to stop. This was 34.1 I'm looking at. At least I like this approach a lot more than what I was doing. But we'll see if I can handle, the next couple problems tomorrow. And I'll see if I can explain this. We're sort of working on this one. But it looks like a one-liner. So I'll address it in the next video. Yeah, I'm gonna call it a day. Thanks for tuning in, ladies and gents. As always, good to see you. Have a great day.